This lesson is a continuation of the circular motion applications that I've been talking about in the previous lesson. And in this lesson, I'm going to be talking about the third and final application of circular motion, which is a mass on a string. So let's consider a simple scenario involving a pendulum. Okay, so basically a pendulum consists of a mass, mass M at the end of a string of length L. Okay, and the top end of the pendulum is fixed, meaning that it's not free to move. If we were to draw it, would look something like this. So let's suppose I've got, let's say, a ceiling here. We've got a mass on a string, mass M, string of length L. Okay, this is pretty much how grandfather clocks operate. Okay, they're basically pendulums, some mass, okay, typically a metal at the end of a string or rope, typically. So what are the forces acting on this mass M? Well, there are two forces, and they are the weight force and the tension force. Okay, the weight force is just the mass of the object times gravity, and tension force comes from the string. It's a result of the string itself. Okay, the force imparted by the string on the mass. Let's also consider this mass on the string. Let's take it to be at some angle theta relative to a vertical, some vertical. And the pendulum rotates with radius r. Okay, r is the center of the circular motion. Some distance below the fixture. Let's call it h, some distance h beneath the ceiling. So we label here mg, the weight force, and the tension T in the string. Right, it's pretty much pulling on the mass, right, pulling it towards the fixture. So we get a diagram which looks like this, something like this. Let's now analyze the forces. Let's look at the vertical forces. We're interested in the vertical forces, so the forces acting vertically. Okay, on the pendulum. So this mass and string system. So we can note down the vertical component of the tension T. We can take it to be T sub y, right? Okay, we're taking y to be vertical, x to be horizontal. And using simple trig, theta's here, t is here, the vertical component will be given by t cos theta. Okay, we've used adjacent over hypotenuse. This is the vertical component here, this dashed line, t cos theta. And we know what the weight force is. So force F sub W, the weight force, is just mg. And these two forces balance. Okay, the weight force balances that of the tension force. That's why the pendulum is able to operate as it is. That's why the mass is able to move around in circular motion. So i.e. t cos theta is equal to mg. There's a better way of writing this, okay, more technically speaking. The sum of all forces, so this is capital sigma, it's a Greek letter, which means sum of in maths typically. The sum of all forces in the y direction is t cos theta minus mg. Why is it minus? Well, we're taking the tension force to be acting upwards, that's the positive direction, and we're taking the weight force to be acting in the negative direction, okay? The negative vertical direction, acting downwards. That's why I've got a minus here. The weight force is minus, right? Acting in the negative direction. Now that's all equal to 0. Okay, it's equal to 0 because t cos theta is equal to mg. Right, and if you take the mg to the left-hand side, you'll get t cos theta minus mg, and that's equal to 0, as we've had down here. And so we can work out the tension of the string using this expression here. Okay, so that implies that t cos theta is equal to mg. And so therefore the tension in the string t is just mg divided by cos theta. So if you're given the mass of the object and the angle of from the vertical, you can work out the tension in the string for a pendulum. Now the horizontal component of the tension force is just sine theta. Okay, I should say it's t sine theta. And this provides the centripetal force, right? If you go back up here, the horizontal component of the tension, if I was to draw it like this, that provides the centripetal force, right? Acting towards the center of motion. We can write also another expression involving the sum of all forces along the horizontal direction. That's just going to be t sine theta. And we can equate that to ma. Okay, that's from Newton's second law. Okay, because the mass m itself is accelerating, right? You get acceleration in circular motion. So we have to equate it to Newton's second law. And so we can then substitute our expression for t into this right here. And so we'll get mg sine theta over cos theta is equal to ma. And that'll just give us sine theta divided by cos theta is just tan theta. Mg tan theta is equal to, this is also equal to mv squared over r, right? Because we took t sine theta, the horizontal component of the tension in the string, to be the centripetal force, and centripetal force is just mv squared over r. And so we get this expression here. We can work out different quantities using this. Right, and the m's cancel out, right, in this case. So you can work out the angle. Let's say if we had the velocity of the mass and the radius of the circular motion, etc., etc. So let's do an example to see how this thing works. So let's suppose we've got a 2 kilogram mass traveling in circular motion of radius 1 meter. And let's calculate the centripetal force, the centripetal acceleration, the linear velocity v, okay, the tangential velocity of the mass, and its period t. So let's do this one step at a time. It's always nice to start off with a diagram, drawing a diagram, if you're not given a diagram, just to make things simpler. So let's draw a diagram. So let's draw a string. Here's the mass. Okay, the radius is 1 meter. It's traveling in a circle, and it weighs 2 kilos. And let's label the forces acting on the mass. So we know the tension force. We know that the tension force acts towards acts away from the mass itself. So let's label this as T. We'll draw an arrow here. Okay, it's the force due to the string itself. We've got the weight force acting downwards, F sub W, which is just mass times gravity. And the centripetal force is acting towards the center of the circular motion in this case. So how do we go about this? Well, we can use the facts that we wrote down before. Let's look at the sum of all forces acting in the x direction. Now we know that if we also let's draw a diagram. So let's put, suppose the string is at some angle theta to the vertical. Let's also suppose We'll suppose that theta is 30 degrees. Let's take it to be 30 degrees to make things easier. Sum of all forces in the horizontal direction is just T sine theta, which is equal to mv squared over r. Sorry, equal to mv squared over r. And let's also consider the forces acting in the vertical direction. That's just T cos theta equals to mg. Let's put 30 degrees for our angle. So we've got two expressions here, expression 1 and expression 2. Now to work out the centripetal force, as the question specifies, we first need to work out the velocity, the linear velocity of the mass in circular motion. So let's do this. Let's do 1 divided by 2. Let's take expression 1 divided by expression 2. So we'll get mv squared over r divided by mg. That's equal to T sine 30 degrees divided by T cos 30 degrees. I'm just substituting everything we know here. M's cancel out, T's cancel out, so we're left with V squared over RG, and that's equal to tan 30 degrees. Sine divided by cos is tan. And then V squared is just RG tan 30 degrees. To get V by itself, we take the square root, RG tan 30 degrees. Calculating that, so R, if you recall, taking that to be 1 times gravity is 9.8 times tan 30 degrees square root, and that's equal to, that's about 2.38 meters per second, 2 decimal places. And so now we can work out the centripetal force. So centripetal force is equal to mv squared over r. We know what m is, it's 2. 2 times v is 2.38, we just calculated it now, squared divided by 1. That gives us roughly 11.33 newtons to 2 decimal places. So we found the centripetal force. Similarly, the centripetal acceleration is just v squared divided by r. That's just 2.38 squared divided by 1, which is 5.66 meters per second squared to 2 decimal places. So we've got the velocity, linear velocity, we've got the centripetal acceleration, we've got the centripetal force. Now let's work out the period t. Now in circular motion, the period t is calculated using the expression t is equal to 2 pi r divided by v. Remember, using this velocity is distance divided by time. Distance in this case is just 2 pi r. Okay, the period is the time, and v is the velocity. So that is then equal to 2 pi times r, which is just 1, the radius in this case, divided by 2.38, and that is approximately equal to 2.64 seconds to 2 decimal places.